in this pre-recorded lecture, we will discuss about quantum mechanical systems, some specific examples of quantum mechanical systems which has a finite dimensional Hilbert space. Now, if we have a finite dimensional Hilbert space, the most trivial one of course will be an one dimensional Hilbert space, but it is too trivial, because when you measure any operator on a one dimensional vector Hilbert space, you will always find it in its eigenvalue, eigenvector, so or eigenkette. So, it will never change with time, or neither in different measurement you can ever get like different outcomes. So, for example, you can think of the mass or charge of a electron. So, they are, whenever you measure, its probability 1 to get a certain number, and that is because you can think it as a one dimensional Hilbert space, at least as far as mass is concerned. But there are other degrees of freedom. The next trivial degrees of freedom, which has a the first non-trivial Hilbert space dimension is 2, and which is the case for electron spin, for example, it is a spin half object. So, we will consider that in some detail, that this will be the our first example of a two dimensional Hilbert space system. So, we will first talk about some general properties of that, some generic properties, and we will deal with some specific examples, which will mostly we will talk about electrons in a magnetic field and connect it with the Stern-Gerlach experiment. But I will briefly discuss that there are many other systems which has exactly same kind of properties, even though they are very different objects for spin, but still they have same two dimensional Hilbert space. So, one of the main rich feature to learn from this segment is that even though there are two problems which are completely different in physical nature, their mathematical structure will be exactly the same if their Hilbert space dimension is same, and some all this thing can be placed under a generic framework, and that is what we will discuss at the later half of this lecture. So, then we may talk about some specific example of more than 2 level, but this is already something which you have done in your assignment. So, this part is not very I will not put a strong emphasis on this part, but mainly I will go over the full details of these 2 level systems. And the next thing we will discuss, which is in the next lecture, is about infinite dimensional vector spaces. So, as you have learned by now that if I have a particle in you want to measure the state of a particle in the position basis, like you want to know the state of a particle at a certain position. So, then you have to consider the position eigenkettes, position operator eigenkettes or momentum operator eigenkettes. If you want to know the energy, for example, you need to consider the energy operator eigenkettes, and those are all examples of infinite dimensional vector space, and that we have already discussed. And we will in the next lecture we will consider specific examples of that, and some of the famous examples are like free particle or particle in a box or simple harmonic oscillator and so on. So, how to proceed? Before you proceed, so you revise once the lecture 9, which is before that, just to remind yourself that what are the rules of the game, and we will basically play the game according to those rules. You will just follow the equations, calculate things and physically interpret that, and all the basic rules which you have to remember, which we built over the previous 8 lectures and summarized in the lecture 9, those rules will come into action now. Okay. So, let me start by saying some of the start by giving some specific examples and some specific calculations which can hopefully clarify some of the pending issues regarding the actual nature of a state in quantum mechanical state and a state gate which expresses a quantum mechanical state. So, in order to do that, let us first understand the property that a state gate is actually a ray in the complex projective Hilbert space. By that I mean the specific direction or amplitude of a particular state gate does not matter, and the only thing that matters is the relative orientation of the state gate with another state gate, with respect to another state gate. So, in order to see that, let us consider a case of 2D Hilbert space, and that means you have two basis vectors, let us say this is 0 and 1. you know that this for the Stern-Gerlach experiment this could be plus z minus z or plus x minus x and so on. But to be general, I am just calling it 0 and 1. So, an arbitrary state gate can be expressed in terms of this. So, it is C1 0 plus C2 1, and let us say I have another state gate phi which is different from this psi. So, that can be again expressed in terms of this two state gates, two basis state gates, that is 0 and 1. And we know since they are forming some base gates. So, they are basically an eigen basis of some operator. In the spin example, there could be the eigen basis of the Sj operator or Scx operator. They must be orthonormal. So, this is the property they must follow. Okay. So, now what do we want? What properties do we want for these state gates? We want this quantity to be some real number and some quantity which is less equal to 1. Why? Because we know that this quantity represents probability amplitude and square of this quantity represents the probability. So, that has to be some real number, let me call it A. And similarly, we want, since they represent probability, we want their the sum of this, which means if I take a inner product of a state gate with itself and then square it, then it will be basically become this coefficient, the probability amplitude squares, sum of the probability amplitude squares, and since they are probability, I want that sum to be 1. And the same I want for the psi state gate. So, if these two conditions are there, let us try to parameterize this C1 and C2. So, they are arbitrary complex number which must satisfy this and this. So, I can write them as some r e to the power I theta 1. If this is r, this one has to be 1 minus r square root because of this property e to the power I theta 2. There is no constant on theta 2 because theta 2 does not play a role in this square. When you take a square, you basically multiply a complex number with its complex conjugate. So, then this angle does not play any role at all. The same thing can be said about the d1 and d2. And now, I want to compute this inner product. So, if I do this compute this inner product, I put these things. So, after one line of calculation, I get here, which is basically like expand this whole form into this. And then I notice that now, if I put this r t theta and everything and do a little bit of few lines of calculation, I reach here after some simplification, and what I get here is some real number plus some real number times cos theta minus phi, where theta is this angle theta 2 minus theta 1 and phi is this angle phi 2 minus phi 1. So, we can see that there are in this expression there are actually truly there are three unknowns, three main unknowns which decides the full form of this square. And this because I want only the, so this and this quantity is entirely real, which is what I also expected. Since this represents a probability, this guy must be a real number, and that real number is parameterized by the quantity r, t and theta minus phi. So, that is the only thing that matters. So, it does not matter what is theta 1, what is theta 2, what is phi 1, what is phi 2, only thing matters is what is theta minus phi, that is the relative orientation or relative angle between these two states. But we know that we know that this thing has to be some number. So, you let us say you know this number from some experiment or by some other argument. So, that means out of these three unknowns there is actually two unknowns, because there is one relation between them. So, now you noticed how much we have reduced the problem. So, the original problem had this C1, C2, D1, D2, they are like all complex number, which means 4 complex number, that means 8 parameter. So, starting from the 8 parameter, we have now reduced to 2 parameters. It was actually 3 parameter, but because of experiments now it is actually 2 parameters. But now there is still 2 parameters. So, we want to still find what these 2 parameters are, and those 2 parameters can be reduced again obtained by more experimental or some other kind of information about a specific system. So, let us see an example. So, let us consider the first Stern-Gerlach setup we studied. The first Stern-Gerlach setup was that I had a psi state which comes to this SGZ device, and it splits into two parts, that is plus z and minus z, and then I take the plus z and plus it through a second SGZ device, and then it splits again in plus z and minus z. And we know that since it is if both are SGZ, then this you will get 100% plus z here. So, if it is n0 here, you will get n0. and if this in the minus z will get 0%, and from there we concluded we can write this plus z minus z states as this plus z minus z equal to 0 and plus z equal to 1, and that is same as minus z minus z. So, now we did a second experiment where we take this plus z and replace the second s z z by an s z x, and we found 50-50 plus x minus x. So, how will I interpret this? So, in order to interpret that, we have seen that we can write this plus z as a superposition of plus x and minus x, and that these coefficients are basically you can think this coefficient as, by using the resolution of identity, you can think this coefficient as a projection of the plus z on the plus x. So, if you want to know what is the possibility here, you have to take the what is coming here and what is this channel measuring and their inner product. So, the probability will be basically square of that inner product. So, that is equal to half, and similarly here also you get minus x plus z square equal to half, and that tells you this actual number, the amplitude is 1 by root 2 times some phase e to the power I delta 1 e to the I delta 2, and this experiment tells you nothing about the phase. It locks down the amplitude, but it tells you nothing about the phase. So, now that the phase is completely arbitrary and it can be anything, and that this experiment does not make any constant on that, I can choose that to be anything I want without hurting any the experimental or the observable facts, and the only thing that matters is this observable. So, for that let me choose the most convenient choice, that is delta 1 equal to 0 and delta 2 equal to 0, and if I make that choice, my plus z is this, and starting from this plus z I can work out what will be my minus g by imposing the constant that plus z minus z are orthogonal. So, this gives me one condition, and minus z is equal to 1. So, that gives me another condition, and putting together these two I get these two numbers for the coefficients of the minus z. So, that is this. So, now that is one choice, and that is perfectly consistent with the experiment and perfectly consistent with the fact that the probabilities are the observables. Now, we do the same thing, we will do the same thing for by choosing a defined delta 1 and delta 2, since they are completely arbitrary. So, when I choose this let us say delta 1 to be 0 and delta 2 to be pi, the plus z becomes this, and by playing this same game here, I figure out that the minus z is this, and that is also a perfectly consistent choice. So, now you can see there are two state gates, two different state gates which represents equivalently the same state or the same state of the system. So, now again I will tell you a little bit later that the word state is not exactly a very appropriate choice of word in this context, but it is somehow this name stuck with this phenomena or name stuck there, but there is nothing which is. So, the English word state represents certain things, and there is no equivalent of that in the quantum mechanics, but still we use the word state and pretend that as if this represents the state, and that is why all these ambiguities are coming and this looks weird. But the point is that you can express these state gates or the state vectors. So, that is a safe thing to say, these are the state vectors instead of saying that they are the state gates. So, you can use the state vectors which explains these experimental outcomes or these probabilities which are the real object in at least two different ways, and actually at least in infinitely many different ways, and that I will come I will make that convince you about that just in a moment. So, let us now make another completely arbitrary choice, which is an even more weird choice. So, when I make that choice, the plus z becomes this very weird object, I plus root 3 by 2 root 2 plus x and 1 plus I minus x, and again I will play the same game, which is I apply this rule that plus z minus z is 0, minus z minus z 1. Then after some algebra I will obtain that the minus z must be this. So, now if I notice that what we just by making the choices, various choices, we found that from experiment 1 and 2 there are all this equivalent way of expressing plus z minus z as a plus x and minus x, and all of them are consistent with the experiment. So, there are, that is to say that there are infinitely many state vector which represents a particular state gates or a combination of particular state gates which is consistent with the observable, which is the probability, not the probability amplitude. So, the probability amplitude is not an observable, and there is no one-to-one correspondence between, like saying this probability amplitude will give me this probability. So there are infinitely many choices. So that is there to say that it doesn't matter what is a particular state gate, how you write down a particular state gate. What it matters that once you write down one, then that determines what the other one will be, because the relative angle, relative orientation matter, and the orientation is that plus z minus z must be orthogonal and orthonormal. So that is the demonstration of that statement. Also you note that it doesn't totally matter if I add put an arbitrary extra global gate, a global phase. So let us say if I put an arbitrary e to the power I pi by 4 here and arbitrary I pi by 4 here, again nothing really matters. So in order to check that, you put that I pi by 4 and calculate these things, and you will see this arbitrary I pi by 4 will not matter. So then just to convince and do a sanity check that this plus x plus z in our product square is half, and that is what we wanted from the experiment or as a probability, and similarly this one is also half. So all these are equivalent and good enough choice, and that is why these things are called projective vectors or rays. So there is a very strict mathematical definition about these projective vectors, which you can check or learn in the mathematical physics course, but here I give you a demonstration of what does it mean. Okay. So now let us take another example and just complete this picture. So now look at the state experiment number 3. So the experiment number, Stern-Gerlach experiment number 3 was z x z. So these 3 of orientation. So the here we know that the z divides into this plus x minus x, and then I take the plus x and divides it again plus z minus z, which represents the first. So the first 2 experiment was nothing exclusive about quantum mechanics, that was just orthogonal properties. We realize that we can also get that similar result if we take balls of different colors and hardness, but this one is the first exclusive result of quantum first exclusive outcome of quantum mechanics, which says if you measure z and then measure x and then again measure z, then the ray seems to have forgotten, the state of the particle seems to have forgotten that it was plus z before. So this gives us the concept of non-commuting observables, and so now let us take the experiment number A and remind ourselves that this plus x. So one more point I want to emphasize, that out of these 3 choices, even though they are equivalent, it is much harder to work with this choice, because obviously the numbers are weird, the algebra will be much difficult and it will be unnecessarily complicated. So since all of these are equivalent, so whenever you encounter this kind of equivalent situation, you should choose the one which makes your algebra much easier later, and that is this choice. So let us do that. Let us take the choice which is A and make my algebra simplest, and then of course from if I choose that, I know what is the minus x. So now for let me just to demonstrate that this choice of plus x and minus plus z and minus z, how does it affects my plus x and minus x. So if I take A, from A I can work out what is the plus x and minus x, but let me for simplicity for again I choose for simplicity of handling or something that I put an arbitrary phase factor. Okay. So let me put an arbitrary pair of arbitrary phase factor and then try to put this this constant to see that what should be the minus x. So if I put this arbitrary phase factor, the minus x will be something like this, or I can have an alternative choice by I can multiply it by a global phase factor e to the pi by 4, then my minus x will become this. And what I wanted to emphasize here, that it doesn't, both of these choice are good enough for given the choice of plus x we made, both of these choice are good enough to explain all the experiments, and this global factor of I pi by 4 doesn't matter anywhere. So that I check by doing this minus x equal to 1 and plus minus x must be equal to 0. So this is the sanity check, and again you can do the same sanity check to confirm that this is true. Okay. Now there is some subtle issues which came out from this discussion, which I want to point out, and this subtle issue is basically what does it really mean by the word state in the context of quantum mechanics. So normally when we use the English word state, it represents a picture, and that is basically a system is in some state, and when you perform a measurement you get to know what is that state. So, and that is also the measurement this word measurement also means a similar thing, and that you do a measurement to know about something about a system, which the system what was before you did not know, and after the measurement you got to know what is the system, like what it was. So, similarly there are associated statements with the words experiment and observation associated. But what I want to see that what I want to emphasize here, that all this from all this discussion, that it is clear that like a state in quantum mechanics is nothing like that word English word state. So, it is like a bad representation or a bad word, and one it won't be wrong to say that it is a good time to think that what or invent a new word for the quantum mechanical state. And basically our language, our English language or any other language are not designed to describe systems which are beyond our normal experience. Well, there are sometimes you can experience some very what will I say, some very subtle emotions or some fine emotions. For that you have some fine kind of some special word to express that, which multiple people like agree that this should be the word to describe a some very subtle thing which is not very easy to perceive. But the point is, this kind of things like a quantum mechanical state is something even more weird, because it is not at all a physical object. So, there is no associated concept like a system was in some state and after measurement you got to know that state. The point is, the system was not in any such state. So, that is the point of quantum mechanical state, because the act of measurement, because as I have discussed this before in great detail, that whether this let us say in this case whether this is plus z minus z, like whether this is plus x minus x or plus y minus y or so on, or it is something else like some infinite dimensional vector space, that totally depends on first of all what you are observing, what you are measuring. So, if you are trying to measure position, then it is then this psi is basically the sum of some position, let us say, let me call it r. So, C r r. So, infinitely many, like r this infinite. So, it is actually some integral sign you represent there and write it as like that. But if you are measuring spin, then it is in this you write it as these states. So, what the system was, so there is no associated concept like the system was in that state and after measurement I got to know what that state is. The system was the act of measurement itself produces the state of the system. So, that is a very fine difference, and the word state does not ring that thing in our head. So, it rings the thing which is completely different from that. It rings like the English word state is not associated with anything like that. That is why the word it is unfortunate that one uses the word state to describe a quantum mechanical, again quote unquote state. So, there is no analogy of that. You can call it something else, like you can call it like instead of using state the word state, you can call it your name or something. So, a state is not really like a property of a system, that is one have to understand. A system, so the base state of the, let us say if I say what is the base state, what is the basic states of the universe, and that depends on the act of measurement, and the act of measurement itself produces that. So, that is like equivalent to saying the statement that the moon is not there until I observe it. So, that is the I thought Einstein quoted this weirdness in nicely. So, so a state is not represents a property of a physical system, but it rather describes a procedure or a prescription to predict that what the system, what will you get if you measure a certain thing in a probabilistic manner. Again, you need the probability also to describe that. So, that is the best possible description of a definition of a state in quantum mechanical sense you can give. And anything, any other attempt, if you try to make it look like any, so we earlier we use this kind of words. So, a state is like this, a state is like that. So, whenever you say it is like that, you try to compare it something you know in classical world or your common sense world. The point is now we should understand that now this crutch of like it is like that, it is like this, is not a good thing anymore, and we will get rid of that. So, we will no longer say a state is like this or like that. You have to just use the word state to represent a. So, the and also to note that we are using the word state to describe a procedure or a prescription to predict the outcome of a particular experiment, and also a state vector. And that is why, since this is not a physical, and then there is one level of weirdness associated with that, that there are infinitely many ways to represent that state as a vector, and that is why these states mathematically are not really vectors, they are rays. And the only thing is mattered, as I said, is the relative orientation between these two vectors, because that is what we demonstrated, that when a system is in one particular state, or like again the quote unquote word state, then you perform one measurement, then another measurement, and their relative relative weight and relative probability amplitude matters, but not itself, the state itself does not matter. So, that is what I wanted to discuss here. So, now one more point I will want to emphasize, that even though the however strange the meaning of the quote unquote state in quantum mechanics, it is the outcome of a measurement, it is still a real number at the end of the day. And we have seen in terms of this Ehrenfest principle, that one can the outcome of the probabilistic outcome, which means the expectation value, follows the classical relations or classical relation between position, momentum, all the classical relations you know. So, however strange the state is itself, the result of a measurement, namely the expectation value, are not that strange, they follow the relation as we expect from CM. So, that we also of course have to ensure, because classical mechanics is a very successful theory. So, whenever you are giving a new theory, you have to make sure that new theory is in sync with the theory you know. Okay, so, this is just a repetition of the point. There are infinitely many ways to represent a state, and the only thing matter is the relative orientation between two states. That is one point to remember. And there is no meaning of a particle being in a state in isolation unless you measure it. So, this word is completely meaningless, as we realize that what state you will find it in is totally depends on the measurement you are doing. And again, this point at the end you must remember this point, although you are using a word state to describe this, but it is not a state in classical sense, it is a prescription to predict the outcome of an experiment, that is all. Okay. So, that was after that discussion. So, let me now try to parameterize it for a two-dimensional system, two-dimensional Hilbert space. Let me try to parameterize a general state. So, we realize that in order to represent a two-dimensional, there is a nice pictorial representation which we will learn here, to represent pictorially the quantum mechanical state of a particle which has a two-dimensional Hilbert space. And this nice pictorial thing is also will emphasize all these subtleties of the state vector as having infinitely many representations or multiple state vectors pointing to the referring to the same state. Again, the state means quote unquote the prescription which can correctly produce the outcome of an experiment. Okay, so, now we realize that in a two-dimensional Hilbert space, we need maximum exactly two parameters to represent an arbitrary state in a two-dimensional Hilbert space, and it does not matter if there is a global phase factor. So, the simplest way we can write it is that a cos theta e to the power I phi sin theta. So, let me call this angle theta prime, because as we realize that this thing must be, these two square of these amplitudes must be equal to 1. So, that is why I can parameterize it as cos theta sin theta, and this can be, there can be a relative a phase factor between them with which is completely general and arbitrary, and what is the common phase factor, that does not matter. So, I can just keep the phase factor in one of these two terms, and I choose to keep it here. So, now notice, so this theta can be 0 to pi and phi can be 0 to 2 pi, and that will span all the possible values of theta and phi, which is satisfying the required relationships. So, then I can naively think that this is an unit sphere, and the point, a point on that sphere represents the state psi. and that means they are represented by these two angles theta prime and phi, and when theta prime goes from 0 to pi, it goes from here to here, and the phi goes from 0 to pi, it goes from here to here, and that way spans the entire circle. But we also notice that this representations is not one to one, because if I say this point is 0, that means the theta is 0. So, that part is vanishing. So, it is the state the base state 0, and if I put theta prime is equal to pi, so I get here, and that is basically minus 0. So, now we know 0 and minus 0 are basically the same state, because they are only defined by a phase factor, and we know that states which differs only by a global phase factor are basically same state. So, this and then we can carry out this statement further. We can see for any theta and phi, if I replace it by pi minus theta and phi plus pi, so that means the diametrically opposite point on this sphere, they represent the same state by the same argument, that one of them is plus psi, another is minus psi. So, then there is some redundancy, and we basically do not need the bottom half this sphere at all. So, all we need is the top half, because the bottom half is just a repetition of the top half. And we also notice that this equator, this entire equator, which is basically e to the power I phi 1. So, that is basically the equator. This entire equator basically just represents one point, which is the state 1, which is the state gate 1. So, that means there is a huge degeneracy, a huge redundancy in the description. So, that we try to smoothen out. One can try to smoothen out by considering defining a new angle theta, which is basically 2 theta prime equal to theta. So, that is the half angle. So, now if I put this in this place, if I use this new angle, it will become psi c theta by 2 0 e to the power I phi s theta by 2. And now this theta is again the same thing. This is basically the angle this point makes with this top z axis. So, now this theta equal to 0, if I put theta equal to 0, this point is 0, and if I put theta equal to pi, this point is basically 1 with this uncertainty of the phase factor. So, now these two antipodal points are basically two orthogonal state, and that you can check from any pair of antipodal points. So, this is some improvement, because now so this the whole purpose of doing this half angle thing is to represent make a one-to-one connection between points on a sphere and a state in two-dimensional Hilbert space, and that is we can see that this is successfully done when you do that. And now moreover we notice that if I do any operation, because we know what any operation does, it takes a state phi to some state psi or something like that. So, this point which is this state which is a point on this Hilbert space, this is also a point another on this Hilbert space. So, it goes from here to here, let us say, and that operation can be understood at some kind of a rotation. So, any operator, action of any operator on this state can be understood as a rotation operation, and eventually also like a time evolution. Let us say I start with this state and over time I traverse some path. So, that can be understood as some kind of a again some dynamical rotation which takes you this point to another point. So, that is we will use that later, we will use this pictorial description later, and that will help us a lot to understand various things, various properties of these states, and have an intuitive pictorial feeling. Again, in principle we can do this again for higher dimensional Hilbert space, but those things are not so easy to visualize. So, this representation of a two-dimensional state gate, arbitrary two-dimensional state gate as a point on a sphere, this sphere is called a block sphere. This representation is called a block representation. So, also notice this map of 2 theta prime to theta, it is an 1 to. So, we said that we initially stated that the whole point of introducing this half angle business is to remind ourselves that we is to get that picture where a point on this sphere represent a state as a one-to-one correspondence. So, notice that statement is not entirely true, because at the point when theta is pi by 2, then this entire equator it represents. So, this map okay, this map is 1-to-1, of course, sorry, I made a wrong statement. This map is 1-to-1, which is basically the correspondence between a point on this sphere to the actual state gate is 1-to-1 for this half angle, but this map, so theta prime to theta, that map is not 1-to-1, because all the points on this equator, all these points in equator just goes to this point, and that is not a one to one. So, that is why this these kind of things are called in mathematical language a 2 to 1 homeomorphism, a 2 to 1 homeomorphism of a SU2 on SO3, and a more technical language one has to say that it is like a moment. So, this is like the SU2 acts like a cover of the SO3. So, we will learn more about this mathematical language later, but this representation is a very helpful representation. Also to notice there this this original point which we discussed earlier, that the spin half systems or this any two level system has this property that when taking the theta, so rotating the theta to 360 degree, then you do not return to this same state. So, if because we normally expect if the theta any angles in a representation goes to 360 degree, we return to the same origin. It does not happen here, and that is because this is represented as theta by 2. So, it 360 degree is like 180 degree. So, to return to the original state where you started from, you have to do a 720 degree rotation, and that is like a special property of spin half or any half integer systems, and that these objects are not, of course, now that we have a pictorial connection between points on a sphere and a quantum mechanical state. So, this could be understood as this Dirac's belt trick, or the trick I have shown in the video where I hold a cup and rotate the cup 360 degree, versus if I hold a cup plus my hand and consider this whole this system hand plus cup as one system, and I rotate it, then it becomes I need to rotate it 720 degree, and there are these objects are called spinors. So, there are many examples of classical spinors like gimbals and all, and they are very useful in certain kind of application like aircraft, like aeronautical engineering and all that. So, we can learn more about that later, but the point is here this half angle representation of 1 to 1 half angle representation helps us to visualize this property of a spin half state or any two level quantum mechanical state, that they do not return to the origin in 360 degree rotation, but return to the origin after 720 degree rotation. So, that is all I wanted to say about quantum mechanical states. So, now let us try to use all these facts to understand the properties of various two level systems.